Number 1. The Bohai 2 Capsize. Picture a drilling rig being dragged across a cold gulf in the dark, its legs raised, its deck low to the water, while a force 10 gale tries to tear it apart. This is the Bohai Gulf, off the northeast coast of China, on the 25th of November, 1979. The rig is called Bohai 2. It is a jackup drilling unit operated by China's Ministry of Petroleum Industry, and it is being towed to a new drilling site because the schedule demands it. The weather does not agree. Forecasts had turned ugly, but the order to move stood, and production pressure won the argument. That decision would kill almost everyone aboard. A jackup rig is built to stand on the seabed on tall legs. To move it, the legs are lifted, and the hull is towed like a barge. In that state, stability depends entirely on the hull, staying watertight and the deck staying clear. On Bohai 2, neither held. A mud pump and other heavy equipment had been left loose on deck. As the seas built, waves swept across the hull and water found its way below through ventilation ducts that had never been sealed for the tow. This is down flooding, the slow, fatal entry of the sea into spaces meant to stay dry. Once it starts in a storm, it rarely stops. The rig began to founder. There had been no serious training for an emergency like this. The life rafts could not be launched in those conditions, and the men had no survival suits to hold off the cold. When Bohai 2 capsized and sank, 72 of the roughly 76 crew died, thrown into near-freezing November water with almost nothing to save them. It happened fast, too fast for any organized abandonment. What makes this disaster strange is how completely it vanished. The story was concealed for months before it surfaced through internal reports and the state press. When it did surface, it became one of the first industrial disasters openly prosecuted in post-Mao China. The Minister of Petroleum Industry, Song Chen-ming, was dismissed from his post in 1980, a rare and public moment of accountability. Investigators pointed at the tow decision, the unsealed openings, and a design that never accounted for towing with loose weight on deck. Historians still debate the exact path the water took. Some accounts put the blame squarely on the unsealed ventilator ducts, while others describe a broader failure of watertight integrity across many deck openings at once. What no one disputes is the speed. Weather records show wave heights and winds well beyond anything the tow plan had assumed as a safe operating limit, and the rig capsized and sank in relatively shallow water almost too fast for anyone to react. Chinese offshore oil development was in its infancy at the time, and Bohai 2 exposed a brutal gap between the country's drilling ambition and its marine safety practice. What is not debated is the lesson. Bohai 2 became the origin point of modern offshore accountability in China, and it forced the country towards stricter standards and foreign joint ventures. It is often set beside the Alexander L. Kielland disaster of the following year as the two grim bookends of one of the worst eras in offshore safety. This was a rig dragged to its death. The next one flipped where it stood. Number 2. The Seacrest Drillship. On the night of the 3rd of November, 1989, a drillship called the Seacrest was working in Unakal's Platong gas field in the Gulf of Thailand. The Gulf is not typhoon country. It rarely sees storms of real violence. That is exactly why what happened next was so devastating. Typhoon Gay came out of the Gulf with a speed and strength almost no one expected, driving winds of more than 100 miles per hour, and waves reported near 40 feet across water that was supposed to be safe. The Seacrest capsized in the dark. The most chilling detail of the whole disaster is what the ship did not do. It never sent a mayday. It never transmitted a single distress call. The best reconstruction is that the vessel rolled over in under a minute, catching everyone off guard and giving no one time to reach a radio. 91 of the 97 crew died. Only 6 survived, some of them pulled from the water after drifting for a day or more among debris and wreckage. For a time, the outside world did not even know the ship was gone. It simply stopped answering. Rescuers searching the storm-battered coast the next day found the overturned hull floating upside down, a smooth steel belly where a working ship should have been. The capsize is blamed on beam C striking the vessel side on, combined with a sudden shift in wind and the ship's own stability limits. In seas like that, a drill ship has very little margin, and Typhoon Gay erased it. Typhoon Gay went on to kill hundreds more people across the region, but the Seacrest was the single deadliest marine loss of the storm. The tragedy raised hard questions. Should the vessel have moved or evacuated before the typhoon arrived? In 1989, forecasting for the Gulf of Thailand simply could not see the storm's rapid intensification in time. There was no modern network of real-time ocean sensors to warn the crew. The exact loading and ballast state of the ship at the moment it rolled remains undocumented because almost no one lived to describe it. Survivors later described the ship rolling over, almost without warning, throwing men into the black water among floating debris and clinging to whatever they could find until rescue boats reached them a day later. Recovery of the dead was slow and difficult, hampered by the storm's devastation along the Thai coast, where Typhoon Gay had already killed hundreds of people on land and at sea. The Seacrest tragedy became a recurring reference in later discussions of drillship stability and severe weather evacuation, a warning about what happens when a vessel with thin stability margins meets a storm no one saw coming. The ratio tells the story on its own. 91 lost out of 97. 6 years earlier, another drillship had gone silent in seas much like these. Number 3. The Glomar Java Sea. On the 25th of October 1983, a drillship named the Glomar Java Sea was drilling in the South China Sea, about 63 nautical miles southwest of Hainan Island. The ship was owned by Global Marine and working under contract to Arco, the Atlantic Richfield Company. Aboard were 81 people, a mix of American, Chinese, Filipino, and Singaporean crew, a snapshot of how international offshore drilling had become. Typhoon Lex was bearing down, and the vessel was riding out the storm on location rather than running for shelter. Then came the last radio contact, and after it, silence. The Glomar Java Sea disappeared with all 81 souls aboard. There were no survivors. When the wreck was finally located, it was found capsized on the seabed at a depth of around 315 feet, lying inverted and partly embedded in the bottom. That inverted position told investigators something important. The ship had rolled over quickly rather than sinking slowly on an even keel. What followed was one of the more thorough inquiries ever conducted into a drillship loss, led by the United States Coast Guard and the National Transportation Safety Board. And here is the uncomfortable truth. They could not conclusively determine what happened. With no survivors and an ambiguous, deeply submerged wreck, the investigators were left with competing theories rather than a single answer. One possibility was progressive flooding through a damaged or open hull fitting, water quietly filling the ship until it lost stability. Another was a structural failure under the storm's loading. A third was a sudden, catastrophic loss of stability in the extreme seas, the ship simply passing the point of no return in moments. Divers and remotely operated vehicles surveyed the site, searching for the clue that would settle it. It never came. The human testimony that could have explained the final minutes had gone down with the ship. The decision by Arco and Global Marine to keep the vessel on location through the typhoon was scrutinized, and the disaster helped push the industry toward clearer severe weather standby practices for mobile drilling units. The investigators examined whether the vessel's watertight integrity had been lost through a failed hull opening or hatch, and whether its stability margins had simply been too thin for a typhoon riding directly over it. The seabed survey, showing the hull inverted rather than settled upright, pointed strongly toward a rapid capsize rather than a slow, controlled sinking. The NTSB report survives as a reference for just how hard it is to find a cause when there are no survivors, and the evidence lies inverted in deep water. It also fed a wider industry reckoning about severe weather standby, forcing operators to think harder about when a mobile drilling unit should ride out a storm and when it should not. The Glomar Java Sea and the Seacrest stand together as proof that the typhoons of these seas can end a drillship without warning. Those failures were the sea's doing. The next disaster was caused by a single weld. Number 4. The Alexander L. Kielland. This is the one that every structural engineer knows, and the one that still keeps them awake. On the evening of the 27th of March 1980, in the Norwegian North Sea, a semi-submersible platform called the Alexander L. Kielland capsized in a storm. It was being used as an accommodation platform, a floating hotel for workers at the Ekofisk field, connected to the Edda production platform nearby. Of the 212 people aboard, 123 died. It remains the worst Norwegian disaster in home waters since the Second World War. The horror of Kielland is not its scale, but its cause. The platform used a design called a pentagon, 5 large columns connected by a lattice of horizontal and diagonal bracings like the struts of a bridge. The entire failure began in one of those bracings, the member known as D6. And the crack that killed 123 people did not start in a great load-bearing joint. It started at a small fillet weld, the weld holding a flange plate that mounted a hydrophone, a sonar instrument, onto the bracing. That tiny, almost incidental attachment created a stress concentration, a point where the forces in the steel piled up far higher than the surrounding metal. Under the endless cyclic loading of North Sea waves, a fatigue crack grew slowly out of that weld. Metal has a memory. Every wave flexed the structure a little, and every flex pushed the crack a fraction further. Investigators later found paint inside a part of the fracture surface, proof that the crack had existed and been growing long before the final night. When bracing D6 finally let go, the 5 other bracings supporting the D leg were suddenly overloaded, and they tore apart one after another. The entire D leg broke away from the platform. In an instant, Kielland lost a fifth of its buoyant support. It listed about 30 degrees almost immediately. Winds were around 40 knots and waves near 12 meters, and in those conditions, the platform rolled all the way to full inversion in roughly 20 minutes. 20 minutes. Lifeboats jammed in their davits at the extreme angle or were smashed against the structure as men tried to launch them. A Norwegian commission investigated and pinpointed the hydrophone flange weld as the root cause, a single bad detail that doomed the whole rig. Kielland became a founding case study in fatigue, weld quality, and stress concentration for offshore engineering everywhere. It drove a hard new principle into design codes. A structure must be able to survive the loss of a single member without collapsing. Redundancy stopped being optional. The rig itself was later righted, salvaged, towed into a Norwegian fjord, and deliberately sunk. One weld doomed Kielland. The next rig was killed by one window. Number 5, the Ocean Ranger. The Ocean Ranger was supposed to be unsinkable. It was one of the largest and most capable semi-submersible drilling rigs in the world, owned by Odexo and drilling the Hibernia field on the Grand Banks off Newfoundland, Canada. Confidence in it was total. That confidence died with all 84 of its crew in the early hours of the 15th of February on number 82 during a savage North Atlantic winter storm with waves reaching 15 meters and more. The chain of events began with something small. A porthole window in the ballast control room, set in a forward column near the waterline, was broken by a wave. Seawater poured through the opening and into the room, and it reached the electrical panel that controlled the rig's ballast system. The wet electronics short-circuited, and the ballast valves began operating on their own, spuriously, without anyone commanding them. This was the heart of the disaster. The system that kept the rig level was now behaving unpredictably, driven by seawater rather than by the crew. The men on duty tried to take control by hand, but they had not been clearly trained in manual operation of the ballast system, and the manuals themselves were inadequate and partly inaccessible. Their attempts to correct the situation made it worse. The rig developed a forward list, and as it tilted, chain lockers and other openings began to downflood. The water kept coming, and the Ocean Ranger slowly foundered. There was no rescue. Some crew reached lifeboats or made it into the water, but the freezing North Atlantic killed them by hypothermia before help could arrive. Survival suits were insufficient in number or simply could not be reached in time, and the rescue vessels could not recover people from those seas. Every one of the 84 died. The Royal Commission on the Ocean Ranger marine disaster produced a detailed report that laid out design, training, and equipment failures together. It found the ballast control room dangerously placed near the waterline, the crew undertrained, the manuals lacking, and the survival equipment inadequate. The Commission's recommendations reshaped the entire Canadian offshore regime, driving major reforms in cold water survival training and gear, and the Ocean Ranger remains one of Canada's worst marine disasters, a permanent wound in Newfoundland. Above all, it shattered the false confidence in an unsinkable rig, showing how a single vulnerable point near the waterline could bring down a giant. It is a textbook study in human factors, the way a small physical breach, an electrical failure, and human error under stress combined into something no one had planned for. A small breach and a big list sank one of the giants. And yet even the largest platforms can flood from within. Number 6. The Petrobras P36. The P36 was, at the time, the largest semi-submersible oil production platform in the world. It was operated by the Brazilian company Petrobras in the Roncador field of the Campos Basin, standing over water about 1,360 meters deep. It was a flagship of Brazilian deepwater production, a symbol of how far the industry had pushed, and unlike the storm-driven losses before it, the P36 was destroyed from the inside on a calm day. The disaster began on the 15th of March 2001 with an explosion in one of the aft support columns. The cause traced back to an emergency drain tank inside the column, which overpressurized and ruptured, releasing a mix of hydrocarbons and water into the column. Minutes later, a second and much larger explosion tore through the structure. That second blast killed 11 members of the emergency brigade who had rushed to respond to the first one, men who went toward the danger to save the platform. The explosions breached the watertight integrity of the column, and seawater began flooding into the damaged column and pontoon. Now, the largest production platform on Earth was slowly filling with the sea. Over the following days, engineers and salvage teams fought to save it. They injected compressed air to force water out and hold the platform up. It was not enough. The list grew worse day by day, and the world watched it happen on the news. On the 20th of March, 5 days after the first explosion, the P36 sank into deep water. The platform had crude and diesel aboard, which raised fears of a major spill, though in the end the environmental damage was more limited than expected. Investigations faulted the emergency drainage system and the design and operation of the column tanks. The platform had originally been built as a rig called the Spirit of Columbus before being converted for Roncador. The loss cost Petrobras hundreds of millions of dollars and forced a serious revision of its safety management, drainage design, and emergency response. The overpressurization of that drain tank was tied both to the procedures around it and to the tank not being adequately protected against the pressures it actually experienced, a design and operational shortcoming rolled into one. Brazilian regulators, through the National Petroleum Agency, scrutinized the operator's practices in the aftermath. The P36 is unusual precisely because its death was slow and filmed, a 5-day structural collapse rather than a sudden capsize, and it remains a case study in how a contained problem in one tank can escalate into explosions, flooding, and the total loss of a structure that seemed too big to fail. Internal failure sank the biggest platform in the world. But the deadliest disaster of all was a fireball. Number 7. Piper Alpha. Piper Alpha is the deadliest offshore oil disaster in history. It was a fixed production platform in the North Sea, about 120 miles northeast of Aberdeen, Scotland, operated by Occidental Petroleum. On the 6th of July, 1988, 167 of the 226 people aboard were killed. To understand how, you have to follow a paper trail because Piper Alpha was not destroyed by a storm or a wave. It was destroyed by a breakdown in procedure. The platform had been converted over the years to handle gas as well as oil, and critically, gas processing sat close to the crew accommodation. On the day of the disaster, a pressure safety valve had been removed from a condensate pump for overhaul, and a blank flange, a temporary metal cover, had been fitted in its place. 2 separate work permits existed for the work around that pump, and here the system failed. Through a breakdown in the permit to work process, the night crew did not know that the safety valve was missing. When the other condensate pump failed, the crew, believing the first pump was ready, restarted it. Condensate leaked from the loosely fitted blank flange, escaped as gas, and ignited. The initial explosion breached firewalls that had never been designed to withstand an explosion's overpressure. What turned a serious accident into a catastrophe was what happened next. A gas riser, a pipeline carrying gas from a connected platform, ruptured in the fire and fed it with an enormous, sustained supply of fuel. 2 other platforms, Tartan and Claymore, kept pumping into Piper Alpha because their operators did not have the authority to shut down, and the fire grew into an inferno. The crew accommodation module, where many men had gathered awaiting instructions to evacuate, filled with thick smoke. Most of the 167 who died were found there or died from smoke and gas. Some men survived only by climbing to the edge and jumping 30 meters or more into the sea. The rescue vessel Theros and standby boats saved many lives, but the scale and heat of the fire overwhelmed the response. The inquiry that followed, led by Lord Cullen, produced a landmark report with 106 recommendations. It condemned the permit to work system and the plant layout that placed processing beside people. Out of it came the safety case regime, a new approach that put the burden on operators to prove their platforms were safe, and offshore safety oversight in Britain moved to the Health and Safety Executive. The reforms went further still, requiring temporary safe refuges. subsea isolation valves to cut off the pipelines, feeding a fire, and a proper way to shut down connected platforms in an emergency. The replacement platform, Piper Bravo, was built with those lessons designed in, and a memorial in Aberdeen still names the dead. To this day, Piper Alpha is the standard case taught in process safety and permit to work training around the world. Procedure killed Piper Alpha. The last disaster was a failure of technology itself. Number 8. Deepwater Horizon. Deepwater Horizon is the disaster the whole world remembers. It was a semi-submersible drilling rig owned by Transocean and leased by BP, drilling the Macondo exploration well in the Gulf of Mexico, about 41 miles off the coast of Louisiana, in water around 1,500 meters deep. On the 20th of April 2010, the well blew out, and the resulting explosions killed 11 workers and injured 17 others of the 126 people aboard. The blowout began deep underground. A failed cement job at the bottom of the well allowed oil and gas to enter the well bore undetected. The crew ran a negative pressure test, a check meant to confirm the well was sealed, and misread the result. The test was telling them the well was not secure, but that warning was not acted on. It was one of the key human failures in the whole chain. High-pressure hydrocarbons surged up the well in an uncontrolled kick, reached the rig, entered the engine rooms, and ignited. The last line of defense was the blowout preventer, a massive stack of valves on the seabed designed to seal the well in exactly this emergency. It failed. Its blind shear ram, the component meant to cut through the drill pipe and seal the bore, did not work. Later analysis found that the drill pipe had buckled off to one side, so the ram could not cut it cleanly, one of several faults in the device. The rig burned for about 36 hours and then sank on the 22nd of April, dragging the riser pipe down with it and making the disaster even harder to contain. Then came the part that turned a rig loss into an environmental catastrophe. The well flowed unchecked for 87 days. An estimated 4.9 million barrels of oil, roughly 210 million gallons, poured into the Gulf, the largest marine oil spill in history. Attempt after attempt to stop it failed, the so-called top kill, the containment domes, the junk shot, until a capping stack finally sealed it in July, and a relief well completed, the permanent kill, that September. The National Commission, led by Bob Graham and William Riley, blamed a cascade of management, engineering, and regulatory failures, citing cost and time pressure and weak oversight by the Minerals Management Service. That agency was abolished, and new regulators, the Bureau of Safety and Environmental Enforcement and the Bureau of Ocean Energy Management, were created in its place. 8 disasters, 1 shared question. Why do they keep happening? To answer that, you have to understand what actually kills a rig. Most of these structures did not sink the way a holed ship sinks, they capsized, and a capsize is a story about buoyancy and balance. A floating rig stays upright because its weight and its buoyancy are arranged so that when it tips, the water pushes it back level. Engineers measure this margin, and it is finite. Every rig has only so much reserve buoyancy, only so much spare flotation, before it passes a point where it can no longer right itself. Downflooding destroys that margin. When water enters spaces meant to stay dry, it adds weight and shifts the balance, exactly what doomed Bohai 2, the Ocean Ranger, and the P36. Worse, water sloshing around inside a flooded compartment creates what is called the free surface effect, which drains stability even faster. Lose a whole column or leg as Kielland did, and a fifth of the support vanishes in an instant. Get hit side on by the wrong wave as the Seacrest was, and the rig can roll past the point of no return in under a minute. The lesson under all of it is simple and unforgiving. Reserve buoyancy runs out, and unsinkable is an engineering myth. Naval architects now model these failures in test basins and simulations, classification societies enforce damage stability rules, and redundancy is built in so that one failure is survivable. But the metal itself can betray you before the water ever gets in. That betrayal has a name. It is called fatigue, and it is the reason Kielland haunts the profession. Metal fatigue is what happens when a material is flexed over and over. Each cycle does a little invisible damage, and a crack grows a fraction at a time. It concentrates wherever the geometry changes sharply, at welds, at holes, at the edges of attachments. On Kielland, the fatal detail was the fillet weld holding a hydrophone flange, a part that carried no real load at all. Yet the stress piled up there, and the North Sea supplied millions of wave cycles to grow the crack. A fatigue crack moves through 3 stages. It initiates, it propagates slowly, and then it reaches a critical size, and the remaining metal fractures all at once. The paint found inside Kielland's fracture surface proved the crack had been growing for a long time before the end. This is why inspection matters so much and why the industry relies on non-destructive testing, ultrasonic scans, and magnetic particle checks that can find cracks before they become failures. Engineers estimate fatigue life with what are called SN curves, and they design for damage tolerance so that even a cracked member does not doom the whole structure. Corrosion offshore makes it worse, eating at the steel and speeding the cracking. Modern rigs carry strain gauges and even full digital twins, computer models updated in real time, that watch for the first hint of it. The whole idea of damage tolerance, that a structure should keep standing even with a crack in it, grew directly out of what Kielland taught. And yet the deepest worry today is aging infrastructure, platforms flexing in the waves years past their planned life, their fatigue clocks ticking somewhere no one can see. Fatigue is a hidden clock, invisible and patient, and it does not care how confident the operator is. Metal fails quietly. People fail under pressure. Because in the end, the most common thread through these 8 disasters is not steel, it is people. Piper Alpha was a failure of the permit to work system, a breakdown in how one shift told the next what was safe and what was not, so that a pump was restarted with its safety valve missing. Deepwater Horizon turned on a misread pressure test, a warning that was there and was not believed. The Ocean Ranger crew fought their flooding rig with training they had never properly received. Bohai 2 sailed into a storm because the schedule said so. These are not the mistakes of stupid people. They are the mistakes of ordinary people inside systems that made failure easy. Safety experts call it the normalization of deviance, the slow drift where cutting a corner works 100 times until the day it does not. Add darkness, cold, fear, and the crush of a real emergency, and even good crews make fatal choices. Behind them sit organizational pressures, the push of cost and schedule from operators, weak oversight from regulators, and failures to manage change as platforms were modified over the years. The P36 disaster even shows the terrible cost of doing the right thing, as an emergency brigade died going toward the danger. The reason the same mistakes recur across decades is that the pressures never really go away, only the names change. When people and metal both fail, the sea finishes the job, and sometimes the sea needs no help at all. Weather was the executioner in the storm-driven losses, and it does not negotiate. Typhoon Gay struck the Gulf of Thailand with a violence that body of water almost never sees, and the Seacrest paid for it. Typhoon Lex took the Glomar Java Sea. North Atlantic winter storms with 15-meter waves foundered the Ocean Ranger, and a North Sea gale set the stage for Kielland. Wave height, wave period, and the pounding of green water on deck all load a structure in ways that can exceed what it was ever built to take. In the 1980s, forecasting simply could not always see these storms coming in time, and there was no dense network of ocean buoys feeding real-time data to a rig. Today there is far more warning, but the hard decisions remain. Should a rig stay on location and ride it out, or evacuate while it still can? Mobile units can sometimes move or disconnect, but fixed platforms cannot run. Engineers designed to a standard storm, often the worst wave expected in 100 years, yet a real storm can always exceed the design. And even with warning, getting people off a platform in a full gale is its own nightmare, as helicopters reach their limits and boats struggle in the swell. There is also the matter of rogue waves, single walls of water far larger than the surrounding sea, which can strike a structure with loads no design anticipated. The gap between the storm an engineer draws on paper and the storm that actually arrives is where these disasters live. Even if the rig holds, the question becomes whether anyone can actually get off it. That question has a grim answer across these 8 disasters. Again and again, the escape failed. Lifeboats depend on release mechanisms that jam when a rig lists too far, and Kielland's boats were smashed against the structure or stuck in their davits as the platform rolled. Bohai 2's rafts could not be deployed in the seas at all. The Ocean Ranger's men reached the water only to die of hypothermia, their survival suits too few or out of reach. On Piper Alpha, smoke and heat sealed the escape routes, and survival meant a 30-meter jump into a dark sea. Every one of these failures forced a change. Modern rigs carry freefall lifeboats that launch even at steep angles. Piper Alpha gave the industry the concept of a temporary safe refuge, a protected space where crew can wait out an emergency. Immersion suits improved and their use was drilled. Fast rescue craft and standby vessels were required and positioned. Workers now train in realistic conditions, including helicopter underwater escape training, learning to get out of a flooded, inverted cabin in the dark. The survival rates in these 8 disasters were so low precisely because those systems did not yet exist or did not work. Each failure wrote a rule that saved the next generation. Taken together, these 8 disasters rewrote the rulebook of an entire industry. Kielland forced redundancy and damage tolerance into structural codes, the demand that a rig survive the loss of a single member. The Ocean Ranger reshaped Canadian training and cold water survival requirements. Piper Alpha produced the Cullen Inquiry and its 106 recommendations, the birth of the safety case regime, the transfer of oversight to the health and safety executive, and new rules for subsea isolation valves and the emergency shutdown of connected platforms. Deepwater Horizon tightened blowout preventer standards and well control practice and led to the abolition of the Minerals Management Service and the creation of the Bureau of Safety and Environmental Enforcement and the Bureau of Ocean Energy Management. The P36 pushed Petrobras to redesign its drainage systems, and Bohai 2 drove the creation of real offshore regulation in China. Behind these specific reforms sat a broader shift, from prescriptive rules that told operators exactly what to do, toward goal-setting regulation that made them prove they had managed the risk. International conventions tightened, classification societies raised their standards, and reporting systems were built so lessons could spread. Every one of these lessons was paid for in lives. The rules exist now. So why do engineers still lie awake? Because the conditions that made these disasters have not disappeared. Platforms are operating past their design lives, their steel flexing in the waves year after year, fatigue accumulating invisibly in structures that were never meant to last this long. The industry drills in deeper water and higher pressures than ever, with more complex and automated systems that bring new ways to fail. And the oldest hazard of all, human error, has proven remarkably durable across every decade covered here. Cost pressure never truly vanishes. Storms are growing more intense in a warming climate. Aging rigs still have to be safely taken apart at the end of their lives, a dangerous job of its own. The finite nature of reserve buoyancy has not changed since Bohai 2, and small details still carry catastrophic loads, just as they did on Kielland. Perhaps the most unsettling fact is that lessons fade as the people who learned them retire, and each generation risks relearning them the hard way. Every one of these disasters began as a safe routine day. That is what an engineer knows when the lights go out. Redundancy, inspection, and vigilance are the only real defenses against an ocean that is exactly as indifferent as it always was. The honest answer is that it can happen again. The sea does not forget, and it keeps the receipts.